sampling. Here we are constructing a Markov chain so that through the Markov chain we're going to get samples from the distribution that we want. Okay? And this is a slide that one of my students have, actually a student who's taking this course designed, and I would like to go through this slide. I think it's a very nice slide. So here is another finite state machine which represents another Markov chain. So this represents this Markov chain. And each of the node here represents either Z1, Z2, or Z3 here. So you have, so let's say, so each of these Z's, I'm going to use, because this sort of, let's say Z prime, let's go say Z prime, right? Z2 prime, Z3 prime, and so forth. Z primes can take either one of these things, Z1, Z2, or Z3. Okay? And the transition probabilities is represented by this complicated transitions. Okay? And it seems in this graph, you can go from Z1 to any of the three nodes. Okay? Or Z2 from any of the three nodes, and so forth. And it's so the transition probability is represented by this thing here. Okay? And after you start with some initial, so Z, I'm going to write Z0. Z0 is a sample from pi. Pi, I've already mentioned, is the probability where you start. You can start at any one of those. You start with some probability. Okay? And then, based on this transition probability, you transition. Okay? And here, the student has nicely, if I take n transitions, so t multiplied by t, n after n transitions, you get something like this. Okay? You get something like this. And so the probability, so you have, so this represents, if you're in state 1, you get probability of getting, state 1, you get the first, so if you're in state 1, the probability of staying there is 0.2, transitioning is 0.3 and 0.5, and if you're in Z2, it's the same. Okay? And so after n, it becomes, it converges, okay? And there's a condition for this convergence. And also, you can also look at it this way. If this transition probability probably has an eigenvector, okay? A left eigenvector. If you multiply by that left eigenvector, you get the same eigenvector, okay? So, if I transition from here and I go through this thing n times, I'm still going to get this. Okay? And here are some examples. The student has actually started with some, so it's assumed that it started the Z0. So here, this represents the Z0 prime, the first one. 3 cases. Z0, 1, 2, and 3. And then we went through the transitions based on this. Okay? So let me just explain what this is. So you do Z1, and let's say you have a three-sided coin or a dice. You roll it. You roll it. And then, so with probability 0.4, it stays there. With probability 0.3, you get Z2. And probability of 0.3, you get also, you can be in Z3. So he went through all of this. So he went transitions. Okay, so he's 1, and then he rolled a dice, and then he got 3, then he rolled another dice, then he got 1, and so forth. Okay? And he plotted. He plotted the the histogram, the distribution of being in state 1, state 2, and state 3. Okay? He also started with another state. And then he went through the whole thing. And he got this. He started with 3, and he got this. So you can see that, and then there's the numbers, 20.1, to actually show you that he actually did this. But you can see that the distribution, no matter where you start, you get the same type of distribution, which is very, very nice. Okay? And previously I had a slide where I did this for many, many cases, and I looked at the slice here. I looked at the slice that way. And that will also follow this type of distribution. Okay? So, let's say my objective is, this is my PZ. Let's say this is PZ. And I want to generate samples. This is easy. But let's say this very complicated distribution represented by some mathematical form. Okay, it's given to you in the mathematical form. You have the math form. How do you get samples from this? Okay? You have to design your finite state machine, or in other words, you have to design it so you get, you have to pick out the right transition probability. So if you go through this, you get that distribution. Okay? So that's the point about MCMC. Okay, that's the general, philosophy. Okay? And I'm going to show you how to generate this transition probability. Okay? Everyone got that idea? So, last time I wanted to do it, but I didn't. Let me just tell you one quick thing. In order for this, in order for this to happen, this type of thing, it must satisfy a condition called detailed balance equation. Okay? And let me just explain what this is. I explained it previously. You start with sub z with this probability, okay? This probability, and then this t represents transition. The book has it this way. As I said, this is a transition from z to z prime. You start with some probability at z, and then you transition to z prime. That is equal to, you start with some probability at z prime, and you transition to z. If that is equal, then you can satisfy this. Okay? So the distribution will be invariant. So you can see that the distribution is invariant with where you start. It doesn't matter where you start. Okay? And after each transition, you get the same thing. So detailed balance equation, and there's a proof that you know, if you start here, you plug in this, you get the same thing. So if the distribution is invariant, you have to get this. In order to satisfy this, you have to satisfy the detailed balance equation. And here is the proof for that. Very easy proof. Okay. So let me just, so you start at Z, you start with Z prime with some probability, and you transition to Z. Okay? And if I marginalize over all possible Z prime, wherever I start, I get a distribution that is the same form as the original distribution. Okay? This condition has to be satisfied. Let me just skip and just, without going to the details, the T that I design, the transition that I design, has to be, must be irreducible. First of all, it has to be irreducible. Meaning that, here you can see that the situation, I have 5 nodes, and there is no link between this cluster and this cluster. I cannot go from here to there. There are 2 clusters. There are 2 clusters. If that happens, this will not happen. Okay? And this is reducible. Reducible into 2 things. Okay? It has to be irreducible. Okay? The transition probability has to be such that have all links. And also, you must not have a cycle. Meaning that you go from here, and you go there, and then from here, there's only one there. So it's periodic, going here, then here, and there's never a convergence. Okay? So again, here is an example of that. Okay, if you start with T, and you let the probability, so if pi is 1/3, 2/3, like this means that you start with probability of 1/3 at Z1, probability of 2/3 at Z2. Okay? If I start with like that and multiply this transition, I get that. Then if I multiply that again to this, to transition, I get the original. I get the original thing. And I'm going back and forth, back and forth. Okay? This is oscillation. So no oscillation. You should not have oscillation. So meaning it has to be aperiodic. Aperiodic. Okay, not periodic. And it has to be irreducible. It should not be reducible. Okay? Okay, now I'm going to skip all this because now I'm going to consider a case. So that the equation that this equation right here, for distribution being invariant or Markov chain to be stable, stationary, if I have infinite number of states, we looked at states. In these states, there were how many states? There were only 1, 2, and 3, right? Here, there's 5. If we consider infinite number of states, then the summation turns into an integral, right? So you start with, at time t, with some probability. You're at time t, and that time, at time t, at state, at state t, have this probability, and based on that probability, you transition to a new state at time t plus 1, and you consider all the possible initial states. Here's integral. You return to a probability distribution that is the same as you started out. Okay, so after each transition, the probability, the marginal probability of that state has to be the same. Okay? And in order to satisfy this, you have to satisfy the detailed balance equation. Okay? Detailed balance equation meaning that you start with this probability and then you transition. Okay? It's the same as you start with z plus 1 probability, you do the transition, it's the same thing. Okay? Whether you start with z plus zt or z plus 1, you get the same thing. Okay? And this is just terminology. I don't know if you had ergodic behavior, meaning that long term. Okay, so let me just actually tell you the algorithm, how this works, okay? Okay, first, you start with some state. State meaning some sample, okay? With some sample. And you have to also define a proposal distribution. Q. What is a proposal distribution? It's some easy distribution that you can get samples from, very, very easily. But this is not only just a simple distribution. You want something that does this. It's a conditional distribution. Proposal Q, which is easy, which is easy to sample from knowing Z. There it is. Okay. So if I know Z, then Z prime, Z star is very, very easy to get. Okay? And one example that people use very often is the Gaussian. Gaussian. So Z prime, Z star is so if I know Z, the mean value is defined. And the variance, covariance is defined. Once these are defined, then this is mean and variance. Then Z star is defined by this Gaussian. Okay? Another way of saying the same thing, is Gaussian. The Z star is equal to mu Z plus some mean. This is some number now, okay? Some number, plus epsilon is some random number that you get as a Gaussian. Zero mean 1. Okay. Sometimes these might be a vector. Okay. So putting in z here and here defines this. You sample epsilon as some zero mean and unit variance. And this z star will have this distribution. Actually, no. Sorry about this. Sigma is wrong right here. If I can represent sigma as L, let's see. Usually as L transpose. This is actually you do it. This is called Cholesky decomposition. Okay. These are lower right triangle. You transpose, this will be an upper right hand triangle. Okay. So this will be L. Or another way of saying this, a lot of people also use a half. So if I was doing it in one dimension, z is a scalar, z star, which I would like as 0 and mu z scalar sigma squared z, then z star is equal to mu z plus epsilon sigma. This is scalar version. Okay? I'm saying the same thing. If I do it this way or this way, same thing. Anyways. So that I've sort of digressed. So you start with some sample, random sample. You define a proposal distribution Q. Okay, it's conditioned on the previous sample. You define it. Then I'm going to go through the samples. Okay, so tau here represents iteration. Okay, and I'm picking n minus 1. So I'm picking n samples. Okay. So here you do 2 samples, sampling. 1, we call the samples I'm going to call U, which is between 0 and 1. I'm uniform sampling. Okay, uniform sampling. Then I also sample from the proposal distribution. Okay, proposal distribution. And if this U is less than this A, then my sample, I accept this sample. If U is greater than that, then my next sample is the sample that I used previously. So instead of using Z star proposed by the proposal distribution, I use the previous one. Okay? Okay, now let me just explain what this is. So this is, you can consider as the transition probability. Actually, it's not the transition probability, but it's not the complete story. So it's comparing, the notation's a little bit different from the book. Okay? There's one way the book explains it. I think there is a little bit of typo also. And in the equation. So the A takes a function of the sample and the previous one. Okay, this is the previous. We're at time tau, and I want tau plus 1. Which will be the next sample for tau plus 1? Okay. So z star and z tau, and I look at this. I compare, this is the ratio that compares, I'm at z tau, this denominator, z tau. By the way, this tilde is both unnormalized. But it doesn't matter if I use the normalized, because the normalization factor, top and bottom, can just drop off. Okay? So this is saying that I don't need to know the normalization distribution. Okay? So the bottom says I'm going from P z tau, and then I transition to z star. Okay? That's what the denominator represents. The top represents from z star, I'm going to z tau. Actually, this might be. And I'm comparing the ratio. Okay? So if this ratio is bigger than 1, the minimum value will be 1, and u will always be less than 1, right? And I'm always accepting. Otherwise, if this is bigger than that, then the minimum value will be this, and let's say it's 0.7, then the probability of accepting z star will be 0.7. Okay? And I could be rejecting that with probability of 0.3. Okay? So this sort of represents the ratio of going from z tau to z star, and the one is going from z star to z tau. Okay? So let me just show you just a little bit of light. Remember the detailed balance equation? I start with some pz. I want to show you this. I have this equation, I think. Pz, then I have tz going to z star. That has to equal pz star going to tz star z. Okay, remember this? This is the detailed balance equation. And I'm going to use p tilde both sides. So what is this? On this side, I'm going from q z to z star, and I'm accepting this with z prime. Okay? And on the right hand side, I'm starting with p tilde, and I'm going z to z star, and I'm accepting with z star z. Okay, that's the detailed balance equation. Okay? So this is the transition problem. This z star, am I going to accept it? I'm going to accept it with this probability. I'm at z prime, and from z prime, I go to z, and I accept it with this probability. And the A that satisfies this is this A. You plug it in and it works. Okay? Okay, so think about this. I don't want to spend too much time on this. So here's MCMC. You initialize, I reiterate, you start with some sample, you define what Q is, usually a Gaussian. Then you go through, I want to pick out n samples, so what do? I sample from unit distribution. I sample from my Z, okay? And I accept this sample based on this A. Okay? If I accept, then the next sample becomes Z star. If I reject, then I keep, what should I say? I copy, or I use the same sample again for the next one. Okay? And this A has also this meaning. If you look at the previous slide, let's say I'm here, okay? The A, if the transition is going to a higher probability, it's going to make it more likely. If the Z that I start, Z star, is in the lower probability, then I make it more difficult. Okay? So the A that is choosing is encouraging samples to be more samples to be sampled from higher distribution than lower distribution. Okay. Any questions with this?
앞에 스테이셔너리 하다는 건 여기서 어디?
스테이셔너리 다시 스테이셔너리 하기 위해서는 스테이셔너리 하기 위해서는 이렇게 정리를 할 수가 있는데, if the distribution has to be stationary, meaning that I move to another state, then that probability has to be the same as the probability before, right? The probability, and that's meaning. Let me just show you this again, right here. So I have many cases with different starts, and if I look at some time, let's say this is ZT, this time T, that distribution has to be the same as this distribution. time T에서 여러 경우를 봤을 때 distribution has to be the same the next time distribution after the transition, right? In order for that to happen, you have to satisfy this. In order for this to satisfy, you have to satisfy the detailed balance equation. And from the detailed balance equation, it's very easy to prove that this happens. Okay? And here again, if you look at it, here, let's look. You start with Z prime. This is sort of a little bit different from the book. You start with Z prime, okay? And from Z prime, you get Z. And then you accept it with this, okay? You plug in this A, move this thing right over here, and I plug this in, so the denominator cancels out, and I do this, and then I extract the other one out, and it becomes this. So you can see that the detailed balance equation has been satisfied. Okay? Which means the distribution is stationary. Okay?
스테이셔너리 할때 매트릭스가 좀 랜덤워크 하다 보면 수렴을 한다 했는데
다시.
초기 매트릭스에서 이제 랜덤워크 할수록 스테이셔너리랑 수렴을 하잖아요.
그렇죠, 그렇죠. t에 n승 하면서 이제 그거 하면서 그게 나오잖아, 그렇죠?
컨버지 스코어라든가 어느 정도의 샘플 포함해서
그것이 있습니다. 근데
대충 100번에서 5분 되는 건지 아니면 그거 확률 Q 디스트리뷰션에 따라서
이거에 따라서 조금 다른 것 같아요. 근데 예제를 한번 볼게요. 예제를 보면은 다양한 경우에 어떤지 있어요. 책에 나와 있는 거. 그래서 okay, so let me just someone asked me about the convergence rate. Okay, and I think it depends on the situation, how you set up your proposal distribution and so forth. So we'll go through this examples a little bit. So the thing here is, okay, so you set up this Markov chain to get the distribution that you want. But I should also like to say that the samples here are dependent. Okay? It's from the Markov chain. It's dependent on the previous. Whereas from rejection sampling, they were all independent, the samples. So what we would like is independent. So, going back to this example here, so it seems like it's dependent. So what do? We throw away the first ones, these, okay? And then, let's say I pick the 10th one, and then pick every 10th one. Every 10th one. And that will make the samples independent. Okay? 10th one of the 5th one. Okay? And that will make the samples very independent. Because this depends on the previous state. This depends on the previous state. So, okay? So that's a comment. And I should like to say that we are transitioning and we are sort of like taking a random walk. Okay? So we saw that, if you remember, this big, this picture that I started out with. Remember this? Here's a distribution and I'm walking. Well, I'm walking random. I could do a random walk around here. Around the Z space. Based on this transition, some transition probability. Okay? I want to do the transition. How is the transition done in this MCFC? I want to transition. It's not just random walk here, okay, which I'm going to show you, but it's sort of random walk, but in an intelligent way. You want a random walk around high probabilities. Okay? That's how the transitions work. Okay? Otherwise, you stay. And I'd like to say, the next slide, this is also in the book, the probability, let's say, I'm doing random walk without considering P. Without considering P, the probability, the distribution that I'm trying to. But let's say my transition, if I stay where I am with 0.5, transition to the right with 0.25, left with 0.25, right? Without considering the distribution, of the P, then on average I will be where I am. I'll be where I am. And the variance, okay, this is on average I will be there, but the variance, one standard deviation is half tau. It's the number of iterations that I take, okay? So I'll be half away. So if I take a random walk around the domain without considering this A, just random walk, then I will be just exactly where I am. And and this is something that I would not like to do, right? And this is not what it's doing. And if you look at this, so here is an example that was given in the book, okay, to show you. This represents a two-dimensional Gaussian. Okay, two-dimensional Gaussian. And so this is where I want to sample from the data. And I've used MCMC. Okay? So I don't know where the starting point is, but I start somewhere here and I'm walking. Doing rest, walking. And these red represents, you know what these red represents? The green represents I accept the samples from the proposal distribution. The red means reject, and I stay where I am. Okay? And if you look, so there are 150 samples that's taken, and 43 are rejected. Okay? So 1/3 are rejected. And here it sort of goes to, if I had a distribution like this, a red one, so the variance across this is sigma max and this sigma min here in this way, and I choose my proposal distribution. So the way I have to choose my proposal distribution very intelligently, Q, such that the variance or the standard deviation is smaller than this. Okay? So this represents the distribution that I want to take samples from. This is the proposal distribution. Well, and the variance that I've chosen for my proposal distribution, the standard deviation of the proposal distribution is smaller than sigma min. Otherwise, if I had a big one, then what would happen? 이게 너무 크면 어떻게 될까요? I'm always rejecting. Because I'll be outside of this. I'll be rejecting a lot of them. So this has to be small in order to go there. And the result is of order of this squared is the number of samples that you would need. In order to keep the injection low. You need to take steps of this order in order to get independent samples. Okay. A special case of MCMC is called the Gibbs sampling. Okay? This is a special case of MCMC. And the way here, there is no rejection. if you use this proposal distribution. What is the proposal distribution? Let's say I have a Z which is m-dimensional. So Z is m-dimensional. It's a vector with Z1 through Zn. So each sample will be m-dimensional. Okay, it's not one-dimensional, it's m-dimensional samples that let's say I want. Then you initialize sums Z, and of course I'm given what P is, and I find the conditional probability. I fixed n minus one of them, and I look at each dimension, conditional probability of each dimension, conditional probability of each dimension, while I'm keeping the others fixed, and I sample. And I take turns until I go through each of the dimensions. You understand this? So here, the sample is m dimension, and I need to get many m dimension. And the way I do it, I sample each dimension from the conditional probability of that dimension. Okay? This is it. There's no rejection here. This is a special case of MCMC, and so the conditional probability is the proposal distribution. This is the proposal distribution, and you are always accepting. Okay. So you are always accepting. So here, let me just say, look, we're back to this algorithm. It's none of this. It's always, I don't even need to do this. I don't need to do this. I'm always accepting. Because I have chosen my Q to be the conditional probability of one of the dimensions. And you may say, is that going to satisfy the detailed balance equation? And yes. And we look at this ratio. So here is going from Z to Z star. You start with PZ. I mean, I could put P tilde here to here, but let's put normalizing factor there and put P. So start with PZ, condition on that to get Z star. This one from Z star, then you transition to Z. That was the ratio in the A. No? If you look at it, now I'm going to divide. So Z star is actually only the kth element. Let's see, only the kth element is updated. All the other ones is the same. That is the same. Okay? Only this one is updated. This one has changed to Z K star. This is what we're looking at. So I've written this notation. I've split this thing up into two things. Conditional probability of the kth element and the rest times the probability of the rest. Okay? This would represent this joint probability. Right? And I looked at this, and QK, let's see, what is this? Let's keep this thing for a while. This one, I've also split this up like this. Okay? ZK, actually it's the element ZK and the rest. And this is the rest. Okay? It turns out the rest, this is the same. Because only the ZK we are considering. So that and that are the same. Here, I'm looking at the sample. So the QK, it should be, okay, so this, QK, so I have the previous Z star, and then ZK. Okay? So this will be ZK. Everything is the same, except for this is ZK and previously. And also this as this is not okay. So this is Q. This actually this can be written like that. Why? Because this is the updated, only the kth component is different. And somehow this has to cancel out with that cancels out with that, and that cancels out with that. It has to do that. This, in fact, is ZK and ZK star. Why is that? So QK, we're updating the kth one condition. So this means our proposal distribution was this. This was our proposal distribution, right? That's the proposal distribution. Right? That was my proposal distribution. I'm given the previous, and I transition to Z, but that's what I'm doing. I want to keep everything the same except for the kth component. That's what I'm using in Gibbs sampling. This is the proposal distribution. Understand what I'm saying? So from the Z star, I'm keeping everything the same except for the kth one, and I'm updating ZK with this probability. Because that's the proposal distribution. And here likewise, we do that. Okay? Okay, so now we're in business. So this probability and this probability is going to be the same. Because it's all, the only thing that's changing is ZK. Otherwise, it's all the same, whether it's Z star or Z. So that cancels out with that. This cancels out with that. That cancels out with that. And then you get 1. So you always accept. Okay? So that's Gibbs sampling. And this is a very nice structure to use when you have graphs, when graph is given to you. Okay? And I'll show you, here it is. See, all these are Z's. Okay? If Z's are given, so in the graph, each of the nodes, the joint probability is represented by the clique. Okay? And if we have neighboring nodes that are given, then we can get this, we can sample from this probability very easily because it's already defined. It's already defined in the distribution. Undirected graph is represented by the product of the clique. Okay? So you just pick out that clique potential and then sample, given the others. Okay? And for directed graph, this is the Markov blanket. You keep all of this the same, sample from that. Another very easy thing, I mean, just look at this right here. This is what I mean. Let's say this is Z1, Z2, Z3. This represents what? The joint probability Z1, Z2, and Z3. What is that? PZ1, PZ2 given Z1. Probability of Z3 given Z2. Okay? This graph, if the graph is given, it's given in this form, right? So how do you sample? I need to get samples for Z1, Z2, and Z3. How do I do that? I initialize this as some number, let's say 0.2, 0.3, and 0.4. Okay, I initialize. And then, how do I do this? From Z1, I sample from PZ1. Z2, what about Z2? The next one. Based on this, let's see, this is the I sample. I take this. PZ3 comes from PZ2. Sample from one. You sample from this, and then based on that, you sample from C2. Then you have sample. Then I hope everyone remembers this. What does this link represent? Right, this link. It's represented by that. That is represented by that. And that is represented by that, right? See, one after the other, just sample. Very easy. So this represents the ith sample. Okay? And you do this many iterations. Okay. Now I'm going to explain. Give sampling is sort of doing this also. If it's two dimension, Z1 and Z2 are two dimension, you're sort of sampling it this way. You're sampling from one dimension. Let's say, so this is x1, sampling one dimension, and then you're sampling from the other dimension. So your sampling path looks like this. It's not like that, okay? Because you're only sampling across one dimension. So it's in a rectangle. Okay, the third sampling method that I'm introducing today is called slice sampling. Okay? So here, this is the book example. Here is a distribution which I would like to get samples from. Okay? So let's say I I start with some value, random variable. What do? Based on this, I do a uniform sampling from 0 to this maximum value, and I get U. Okay? So I start with some sample, I sample U, and that will sort of tell you where you are. So let's say that U, if this is considered 0 to 1, U gives me that. What do? I sample again across this slice. Okay? So it's two sampling. One you sample from here. I have the algorithm in the next in the slides. So you start with here. You assume that this is uniform. You sample. You get U, and across this slice. Okay. This slice may also include here, but to keep it simple, you look at the slice or interval that it includes the Z star. Okay. Like that. And you sample, which gives you a new Z. Okay? So there's two ways. You start with someone, uniform sampling, and then you do a uniform sampling across this interval. Okay? If it lands within these two intervals, then you accept. If it lands out, you move the interval. You adjust the interval to make it shorter. And then you sample. Okay? And then you repeat that procedure. So essentially what I'm doing is I'm sampling, so I'm considering this thing as a two-dimensional space, and I'm sampling all the points in here. Okay? So that's slice sampling. But you may have a question. I had a question too. So you start with somewhere, you do a uniform sampling, you look at that interval, and then you do sampling. If it's outside, you throw away. If it's within this interval right here, you accept. And that will be a new thing. And then here again, you do uniform again. It seems that you're only going to stay here in this thing, right? If I do slice sampling. But there, you need to sample from here as well. When does that happen? That happens when you're down here. When U is like that. When the U value is here, you get a long interval like this. Then you can move to this portion. Okay? That's slice sampling. Let me let's see, adaptive. So if I ask the TAs, I'll give you this slides. I've asked some of my students and the TAs to actually do the MATLAB, okay, to see the performance of these things. So I'm just rejection sampling. Let's say this is the distribution that I want. Okay. In fact, this is two Gaussian, mixture of two Gaussians. One dimension, and here the dotted line represents the proposal distribution. Okay? here's a red one. Let's say whenever you are in the red line, you reject. You throw away the sample. Whenever you're in the green line, you accept. And this is a Gaussian. It's very, very easy to use. And you are rejecting a lot of samples. Oh, and you're rejecting a lot of samples. 몇 개 샘플이 rejected는지 있나? Okay, so about half the. So, because there's a huge gap between here, so you see that there's a lot of red. You're rejecting it. So there's adaptive sampling, where you look at the grid, okay, and then draw a tangent, okay, which leads to an exponential function. Okay. And then you do sample from the red distribution. So by the way, this we are looking at the log of the probability. Okay, log of the probability to sample. And we can use transform technique. Remember, the line in the log domain leads to an exponential distribution. Okay? And we can do rejection sampling to get that. So that's what we did 2 lectures ago. And this is Metropolis Hastings. That's, oh, I forgot to say, this is an MCMC. This is a generalization of all the distribution. Okay. So MCMC, the most general MCMC algorithm is called the Metropolis Hastings algorithm. Okay, and I didn't say the name. So you start with some initial value, proposal distribution. Here, a Gaussian is used. Okay. So a proposal distribution depends on the mean value of the previous one. Okay. And then you calculate. So the sample that you get from the previous, you update. You also use this to calculate your xi's, okay, that probability. And then you look at you calculate your A based on this. And you sample again U and compare it with this A value. And if U is less than A, then you accept. Otherwise, you stay where you are. Okay. And this is the samples that it's transitioning. And you can see that you start from here, you transition to very high probability. It's the proposal distribution give you this red one, let's say. It will not go down, it will reject. So this red represents reject. Okay? Whenever it gets something really high, it accepts. Here, it's going to a lower probability. It could accept, but the probability is very, very low, so you probably reject it and stay with it. Okay? So that's what it. This is give sampling. So give sampling you usually use when you have a high dimension data. Okay, so you sample from each dimension. Here, a 2-dimensional Gaussian is shown. Okay, and so here the dimensions are labeled in X rather than Z's. Okay, and then you look at the conditional probability of each dimension, okay, and then you sample. Okay. And this is looking at this way, I think. So here is dimension 1, this is dimension 2, that's the probability in 2 dimension. It's looking across it's fixing one dimension, okay, and it's looking at that probability. So that's represented by the yellow one right here. Then it samples, then it fixes that, and then it samples from the red one. So it goes this dimension, sample from that dimension. And here is slice sampling, the algorithm. I'll give you this or this. Okay. So you start with some initial value, okay, and you choose some step size, W, okay, or interval, and you sample. So you start with x1, let's say x1 is right here. You sample U, so it's sample, uniform sampling from here to there. Okay, that's that. And then you sample again from uniform, 0 to 1. Okay. And you consider intervals, okay? X min and X max, right here. Okay. And X min and X max, based on this value here, so X min and X max is calculated. And then you do uniform sampling in that interval. Okay. And if it's within here, then if it falls within this interval, then you accept, otherwise you reject it and change the interval again, and you sample again. And you can go from this hill to the next hill if you come down a little bit lower. And then you run this. And this is rejection sampling. Okay, here is rejection sampling. This red one, blue one, I'm trying to get samples from. This is 100 samples. This is 1,000 samples. This is 10,000 samples. And you can see that 10,000 samples represent that very well. This is adaptive sampling, and in adaptive sampling, you can only use it when the distribution is log concave. Log concave. So if you look at the log scale, it has to go like this. This is not log concave. This is not log concave, right? So you can't use adaptive sampling here. This is log concave, and you can see that 100, 1,000, about 10,000 samples. You have very good approximation of that. This is Gibbs sampling, okay, in 2 dimensions. It's 100 samples, 1,000 samples, 10,000 samples, and you can see that a lot of them. Okay. These programs are very, very easy to implement. It's one of a couple of them. Okay. And I would like to remind you, why are we getting these samples? Because the integral is too difficult. So you get these samples and you plug it in to get an approximation. Okay?
무슨 MCMC 샘플링 정확히 언제 사용하는 다른 샘플보다
MCMC 거의 MCMC는 항상 사용해요.
저런 것들은 어떤 거가 안 들어가서 사용을 안 하는
어떤 거요?
저 지금 나와 있는 샘플
이건 rejection sampling. 이게 제일 먼저 나왔고 이거의 문제점. I've already said this. It's a problem. You're rejecting a lot of samples because if the if the distance between here and here is big, you're rejecting a lot, right? Right. So then there is adaptive sampling, but this you can only use when the distribution is log concave. Metropolis sampling. Oh?
제일 제너럴하게는 사용할 수 있는 거.
Metropolis Hastings sampling. Okay? But I should tell you, 그 convergence rate를 정확하게 말했는데 it's slow. It's slow. Because you're sort of doing random walk, but random walk in the high probability region. Not just random walk anywhere, but in the high region, high probability region. Okay? But it's slow. Okay? And Gibbs sampling, okay, when you're given a graph, then Gibbs sampling is almost always used. Here you don't reject anything. But you have to know the conditional probability. Huh? The conditional probability of each dimension. So let me just say about this conditional, just remember, yeah. Okay, so the, oh, yeah. So this is a stochastic way of doing the integral. There is another way called variational inference, which is not based on sampling. It's based on simplifying the equation that you're trying to do the integration, whatever. By making samples, making the random variables independent. Okay, so I will put up the slides, okay, and ask the programs, MATLAB programs, to be uploaded so that you can play. Okay, so that finishes sampling right now. And next lecture will be on reinforcement learning. I won't have much time. I know there are courses on reinforcement learning. Okay? So this will be a basic sort of overview. Okay? What reinforcement learning is. And then I will probably try to finish off. Okay? I know it's 11:52. I would like to say that we're very close. We have 1 or 2 lectures left. That is projects. I tried to convey a lot of important ideas in machine learning. Okay, we looked at 2 books, which are very good books. I chose from the many topics there are in machine learning. I chose those topics that I thought was very, very important, okay? Which coincided with many of the recent book on understanding machine learning. Okay? There are still topics that we need to cover, but we don't have time. So all my lectures are videotaped, so that you can come. I tried to fix the scribes. I asked you to scribe it so that to help you understand the material. It's a little bit late, but I've been doing scribes. We had some very difficult homeworks. Okay, and the reason I made those homework very difficult is to give you, more practice and I wanted you to see topics that are outside this, the topics that I've taught, okay? Topics that are but related. And this project that you're doing is probably going to help you, because we learned a lot of theory in class. Project will give you the opportunity to actually implement. Okay? So, next week, I think 1 or 2 classes and we're done. Oh, another thing. At 4 o'clock, in the KI building, second floor, I think it's Maze, there will be an invited speaker from Microsoft, and he will be lecturing about deep reinforcement learning. Okay? So, anyone who's interested, please come by. Okay? It's on the second floor of KI building. Okay, that ends. And I asked students to evaluate the course.